Okay, so for this part, what we'll do is we'll focus on analysis of exploration strategies. So far we have looked at how RL algorithms behave in terms of optimization error and sampling error. However, in this part we look at how does data collection affect the performance, where we don't have access to an oracle like the generative model which can collect its own data. So in this part, what we'll do is we'll not look at RL because the analysis of RL exploration algorithms tends to be somewhat complex, but we'll look at multi-armed bandit problems. And this is in a sense one-step RL. And you've looked at this in the exploration lecture, but I'll briefly recall what a multi-armed bandit looks like. So we have n possible arms or actions. So you have these arms or actions a1 to an. In round T, you would pull the ith arm and observe the corresponding sampled reward. So we assume that the rewards are stochastic, but the expected reward is something that is given by R bar for each arm AI. And you are observing a stochastic sample from this distribution D over AI, which specifies the reward function distribution at each round T. And what you do is you observe this reward and you record it. And you use this to train, or you use this to obtain a good strategy for the bandit problem, for the future steps. What you really care about in this setup is the regret metric, which is defined by the total reward you would have gotten if you took the best arm in hindsight, which is A star, minus the sum of rewards you have gotten for AT, for the arms that you pulled over time. And in a sense, what this is saying is you are like how much you are losing by not picking the best thing to do. And note that this does not consist of sample reward. It consists of expected rewards because that's what is the quantity you care about. Whereas sampling reward is just sort of a nuance of the system that it gave you a sampled reward. So again, as we discussed in the very beginning of this lecture, if this regret grows sublinearly, then we are converging to the optimal action as infinity, and we are learning efficiently because it cannot just arbitrarily converge to the optimal action. It has to consistently converge to the optimal action, which is a good thing. Just sort of a slight detour here. If you want to do this for RL, you can think of reward functions being mapped to the value functions. So you have, instead of R, you have the value function, and you can think of T as episodes. So sort of the same notion holds true there. The analysis is similar, but it does not transfer. But more or less, things are somewhat similar. Okay, so how do people do exploration in multi-armed bandits? So this is also something that was covered in the exploration lecture. And it's something called optimistic exploration or upper confidence bound algorithm. What it does is, let's first define NT of AI as the number of times an arm was pulled. Let's define R tilde T of AI as the running average of the observed sample rewards for arm AI. Now, the UCB or the optimistic exploration algorithm would say that in round T, you should pick an arm AT such that AT is the argmax of the sampled reward R tilde T of AI plus a bonus term, which is given by this complicated expression that you see on the slide, which is log over 2 nt divided by delta by twice the number of times you've seen an arm to be pulled. Capital T is the number of total iterations you would do for this bandit problem. So that's the total number of iterations you are looking at. You want the regret to be small for, and N is the number of total actions or total arms available to you. So it's mean reward plus a reward bonus. So where does this reward bonus sort of come from? Like who designed this reward bonus to be of this form, and why is this a good algorithm? That's the next question that we intend to answer. So just by its appearance, this reward bonus should make you remember concentration inequalities, because this log 2nt over delta divided by the number of times you've seen something is sort of very reminiscent of concentration inequalities, right? So what we can do now is we can sort of obtain this bound directly by applying any general concentration inequality like the Hevding's inequality. So what we can do here is we can say that with high probability, which is more than 1 minus delta, for all possible arms 1 to n, that is index I, for all possible time steps 1 to t in the interval that you're looking at, in the interval you are looking at the regret, for all those time steps and for all those arms, turns out that this reward bonus that you're adding is basically the bonus you would obtain for a high confidence, or basically the bound you would obtain for a high confidence bound coming from Hevding's inequality. So R tilde t is close enough to R bar AI, which is the actual mean reward for that arm, and the difference is bounded by B of AI, where B of AI is given by this quantity. So that's sort of the reward bonus part. So the reward bonus turns out to be the right hand side of the Hebding's inequality, or the constant you would get with which the rewards are bounded in Hebding's inequality. Yeah, the Hebding's inequality, you can look at the similarity that you see here. Okay, so why was this actually useful, or why is this connection to Hebding's inequality actually useful? So first of all, let's rewrite this connection in this without the absolute values. So what we can say is the R bar of AI is bounded by R tilde of AI at any time t plus the bonus you give at that time. And similarly, it's lower bounded by the mean reward minus the bonus you give at that time. This is a direct consequence of the absolute value bounding from the Hebding's inequality. And what we can say is that with high probability that the true reward for any arm lies in this interval which is defined by the bonus. So for any arm AI that you want in your system, you have these bonuses such that you can construct these lower bounds and upper bounds. And because these lower bounds and upper bounds are constructed with high probability, like you cannot say this for certain, you can only say this with high enough probability. This is basically a lower confidence bound and an upper confidence bound. So confidence comes in because you're the high probability bit. So how can you use this how can you use this fact to obtain a bound on the regret? So it turns out that it gives us a very convenient decomposition, a convenient bound on the regret. That is also a good bound. So remember that the regret was basically the suboptimality that you incur at each iteration because you're not playing the optimal arm A star. What you can do is you can use the fact that for every arm in your system, and A star is also an arm in your system, the mean reward is upper bounded by the upper confidence bound that you see on the top of the slide, and the mean reward is lower bounded by the lower confidence bound. So what you can do is for R of A star, you can apply the upper confidence bound. For R of AT, you can apply the lower confidence bound, and that's going to be an upper bound of this regret. Now note that the arm that you are choosing at time t is precisely the arm that maximizes the mean reward plus the bonus. That's the algorithm. That's what the algorithm does. So agnostic of A star, AT, or the arm that you pulled at time t, basically maximizes this upper confidence bound, or R tilde plus B, essentially. So what you can do is you can upper bound this regret further by choosing AT in there. So you can say R tilde of A star plus BT of A star is upper bounded by R tilde of AT plus BT of AT. And why did you get this? You got this because the arm that you choose at time step t literally maximizes this expression R tilde plus the bonus. So that's how you get it. Now things are very convenient looking because it turns out that you can essentially just cancel off R tilde of AT and you can get a sum over bonuses. So sum over BT of ATs. And now if you recall from the previous slide, the expression for bonuses or expression for these reward bonuses are essentially dependent on the inverse square root of counts. So inverse square root of number of times you have pulled an arm AI in your system, right? So because of this bonus structure, something that you can kind of show by using algebraic manipulation, and this is left to you as an exercise, is that you can show that the overall value of this bonus is something that is of the order of square root of t. So it is some constants multiplied by square root of t, or it's less than some constants multiplied by square root of t. You also get a multiplication for the number of arms in there, but that's just coming out because of algebraic manipulation, and that's just a constant at the end. What it really matters is it's a square root of t function, or square root of t log t function, rather than something that is linear in t. And that says that it's a good algorithm because our aim was to obtain order of root t like guarantees for the method in here. Now, one thing that is and this is left to you for an exercise, and it's not too hard. You just need to reorganize the terms in a way that you can sum up. You can compute a good bound on the summation of the bonuses, and that's basically it. Now, one thing that is missing here is the fact that all of this analysis that we did here is going to hold true only with high probability. So this is not going to hold true every time, right? So what is the regret that you get when this bound doesn't hold? So this is, let's say this holds true with probability 1 minus delta. So what happens when you're not able to get this bound to hold and you actually incur more regret? So for that, what we can do is we can simply say that we add a delta plus delta t term here. Why do we add that? So note that the delta, note that the regret bound holds true with probability 1 minus delta. So with probability delta, when this doesn't hold, let's imagine the worst thing which can happen, which is you incur a linear end time regret, because you are always playing sort of the arm that is or you're always playing an arm. Let's say your difference between the optimal arm and the arm that you played is, let's say, a constant. That means that you will incur an additional term that is linear in t, because at each step you're incurring a constant. That means when you are summing over t, you are incurring t times that constant. And for now, that for without loss of generality, assume that that constant is equal to 1, because that just removes the number of constants from here. Or you can think of it as an order term. So you can think of it as delta times big O of t, which means it's of the order of t. So what you're doing here is you're just incurring an additional term that looks like delta t in the case when the high probability regret bound does not hold true, and the probability with which it does not hold true is delta. What you can do now, so what we've shown so far is we've shown that the regret is this term that looks like order of square root of t times log t, and log t is typically ignored, or log t is typically smaller than t, and hence you can just consider it roughly as t, plus delta times t. Now, it turns out that the first term is sublinear, as you can clearly see. The second term, it's linear, or it appears linear, but delta is really up to us. So what we can do here is, if we know what capital T is, we can simply set delta to be something that is let's say smaller than 1 over t. So if we set delta to be equal to 1 over t, we just get 1 over t times t, which is a constant. So we only incur a constant additional term if we set delta right, and delta is really up to us to set, because we are talking about a bound that says with high probability, where the probability with which we are guaranteeing high probability is up to us. So what we have shown so far is that by ensuring that we are optimistic, that's by ensuring that we add bonuses so that suboptimal arms look more optimal and we explore them, and by also making sure that our choice of reward bonus is such that the optimism, or the amount of extra error that we're incurring, which is the 2 summation of bi's that we saw on that slide, if they decay at the right rate over time, then we can get good performance, because we get good sublinear regret. And similar analysis also works for RL, though it's a bit more complicated because we have MDPs, sequential transitions, and so on. Although the skeleton is quite similar. So you still look at sort of the difference between the upper confidence bound and the lower confidence bound. That's typically for the value function there. You need to bound that in a way. But essentially the skeleton of the proof is very similar. And for instance, the reward function will become the value function, T will become the number of episodes, etc. Okay. The final bit that I want to kind of briefly touch over is the bit on reinforcement learning with function approximation. So far we've seen that with general function approximation, let's say if you represent a Q function as a deep network, you cannot really get any guarantees on convergence or divergence, or even sample efficiency, meaning that you might need infinitely many samples to solve for the RL problem there. So under which special cases would RL still work with function approximation? That's what we want to look at here. And the reason here really is to just build intuition for what kind of practical sort of assumptions or practical scenarios would be good for applying RL algorithms in, or which RL algorithms might work in which practical scenarios. So let's consider the simple setting of policy evaluation, where you are using, where you're trying to kind of do TD or fitted Q iteration or fitted Q evaluation to find out the value of a policy. So it's not exactly TD learning because you're not learning values, but we are learning sort of a Bellman, we are trying to train a Q pi estimate. Let's imagine we are doing this with linear functions. So we have W transpose phi of SA, which is what our Q function looks like, where phi of SA is some feature vector given to us, W is a learned vector that we're trying to learn. So what happens is, if we assume here that the linear function class, or the function class W transpose phi of SA that we have, it can represent the exact Q function. So it can represent Q pi, meaning that there exists a W star such that Q pi is equal to W star transpose phi of SA for all state action pairs. If this happens, then this converges. So this can give you the right solution. But if this doesn't happen, so the Q function is not expressible in the linear function class, then divergence would happen here. So it would diverge back to something which is bad. So it basically says that if you can make the assumption that you can exactly represent the Q function for the policy in your function class, then things are going to be good. And remember that this is not saying anything about neural networks because it's still a linear function. And here when we do this training, we are assuming that we solve linear updates, and we're not really doing gradient style updates here. So remember that it's not really talking about the neural network function class, which can behave somewhat differently. And we haven't really understood that exactly because the theory of deep learning with neural networks is still being built upon. Now, what about RL with function approximations? So this was the more like policy evaluation. You're given a policy pi, compute q pi, that was the result there. What about online reinforcement learning algorithms? So this paper from Wen and Van Roy in 2013 showed that if you have a deterministic MDP, which means the transitions and the reward functions are deterministic, and some other assumptions that they made, and you have a linear Q function in the sense that there exists a linear weight matrix, W star, such that the optimal Q function is linear in this, or can be exactly represented in this linear function class, then RL is sample efficient in the sense that it would not require exponentially many samples in the horizon to solve for the optimal Q function. Similarly, another bound that was shown was that if you have approximate linear Q pi for all policies pi in the MDP, which means that you can roughly represent Q pi using a linear function over some features for all possible policies in the MDP. So consider all possible exponentially many policies in the MDP. And the data distribution, if it covers all policies, which is defined by this assumption, you will find in the papers that I linked, then you would require only polynomial in the horizon many samples when you have wide initial state distributions, or when you use a generative model, which means if you have enough coverage over your state space and you can start from enough regions such that your data distribution that you generate by running, that you're optimizing over, sort of covers all policies enough well, or in a good way enough, then you will find, and your Q function Q pi is linearly representable, then you will find that you can get polynomial sample complexity. So it's really a strong assumption because you want your data distribution to cover all policies, you want wide initial state distributions, and you want Q pi to be linear, or to be approximately a linear function for all pi. Then there's this recent paper from Simon Du et al. In 2020 that shows that if you have approximately linear Q star, which means that the optimal Q function, it is close to, or it can be represented approximately well enough using your linear function, but not exactly, then you cannot converge. You'll find that you need more than polynomial, exponentially many samples to be able to learn a Q function. And when I say exponential, it's really exponential in the horizon. And really the strong point which all of this tells us, or this last bit tells us, is that that this result is not quite true when your feature representation phi of SA is informative, means that it can predict the function very well, which means your Q function or Q star function can be represented under this representation to good degree of accuracy. But along with that, if it is also compressed, means that the dimensionality of phi is small enough. In that case, approximate linear Q star works. So there's this other paper that shows this, that if your feature dimension is compressed enough, then it works. However, if it is not compressed enough, the Du et al. 2020 paper says that it does not work. So you need exponentially many samples in that case. And there are many more assumptions here which talk about different structural assumptions in the FDP, which you'll need to be able to find convergent or efficient algorithms here. One last bit that I would like to say here is that this bit about compressed enough representations is somewhat interesting because a lot of the work in image-based RL has really focused on finding sort of compressive representations for the image and use that for the RL part. And if you do that, it really probably, I mean, maybe this theory kind of somewhat explains or tries to explain something like that, because what it really says is that if your representation is compressed enough and it can represent the Q function, meaning that it's informative of the MDP, then you can do good or efficient RL. But if it is not compressed enough, which means let's say it's a full image, or let's say it's some vector that is kind of high dimensional, then maybe things are hard. So that's somewhat of an interesting point. For for a more collective table of all such characterizations, I would recommend you to see this paper that I cite on the slide below.